Well, hi, everybody, and welcome. This is Calling All Systems for October in 2023. The name is Models in Space. So I'm Barclay Brown. I'm your host for today. And may I say, we just have to begin by saying space, the final frontier. These are no, all right, that's enough. But it really is exciting to be talking about the theme of space, because in a very real sense, it is kind of the final frontier to a lot of our science and so forth. And it's right on the edge. So I'm going to start by acknowledging our sponsors, which I have right here. So Dassault Systèmes is our sponsor for the series. All right, let me introduce our panelists, and then we'll jump right into to why you came, which is to hear all the interesting discussion here. So going in alphabetical order, starting with Stephanie Sharo Chiesi, Director of Digital Engineering, Design and Prototype with Blue Origin. So Stephanie's a CERC, that's the Systems Engineering Research Center, doctoral fellow at Stevens Institute of Technology in the School of Systems and Enterprises. She's currently the Director of Digital Engineering, Design and Prototype at Blue Origin. Prior to joining Blue Origin, she's had senior roles in systems engineering senior roles in aerospace and defense, including at SAIC and Raytheon Missiles and Defense, at Paragon Space Development Corp, and at Draper Labs. She's a CSEP and also an inventor with 5 awarded patents, and has two bachelor's degrees, aeronautics, astronautics, and biology, and then a master's degree in aeronautics and astronautics, all from MIT. Francesco Dazzi, welcome, Francesco. Thanks for being here. He's a certified systems engineer and project manager with an educational background in physics, has more than 20 years of experience, mainly dedicated to the construction of ground-based telescopes and technical management of scientific projects. Francesco is the current president of the Italian Association on Systems Engineering, that's AISE, and that's also the INCOSE chapter in Italy. So thanks, welcome, Francesco. Dr. Saulius Pavalkis, who goes by Saul now, we call him Saul, has 20 years experience in MBSE solutions experience. He's a product owner and analyst at the Cameo core team and the chief solution architect, consultant, and trainer. He's an expert in MBSE ecosystems, digital engineering, system architecture, and simulation in aerospace, defense, automotive, and other industries. He's kind of Mr. Cameo. He's in the core team, was one of the original inventors, I think, even of Cameo. So he's an expert on that side of it. And welcome him. Of course, he works for Dassault, and Dassault is the sponsor, right? So there we go. Next, Lucio Tirone is an ESEP, expert systems engineering professional, and OCSMP, which is the OMG certified systems modeling professional, and lead engineer at SKA Low AIV. Has 20 years of experience in applying model-based systems engineering to conception, design, development, and testing of complex systems in various technological domains, including defense, space, maritime, transportation, and security. He's currently assembly, integration, and verification lead engineer and deputy senior PM of the SKA Low, which is a low-frequency radio telescope under construction in Western Australia. He's a former director of INCOSE in the EMEA sector and also president of the Italian chapter. He holds INCOSE ESEP certification and also the OMG system modeling professional certification. So welcome, panelists, and glad you're here. But let's just jump right in, see if we can make this interesting. So first of all, when we think of models, right? And we do deal a lot with models in systems engineering. And I wonder if you could comment on this. It seems to me that sometimes we are confused in our language, because are there different kinds of models? We tend to say modeling is this, but does that assume that all models are the same and behave the same? So let me sort of start out with that. How do you, in your businesses, in your thinking, and your attitudes, think about different kinds of models, and what makes sense to you to sort of categorize models? We can start with whoever'd like to go.
Maybe I could start.
Sure.
Definitely there are 2 types of major models. Not necessarily the limitation is here, but we have descriptive system architecture models, right? And that could go also to the design. You have CAD, which is descriptive model, right? So what's the descriptive part? So you describe in system architecture functions, interfaces, parameters, right? So how the system shall behave or behaves. What are the interfaces like requirements? What are the functions like requirements? But it does not answer the question how this will perform. The performance side, that's analytical models. So those would be like created based on specific analysis type. So that's the big difference. And I think there is a common confusion. We take analytical models and we say, okay, we do model-based system engineering. And that's the lowest level of maturity, I think, because they were available all the time in the market. And you don't connect them to system architecture. But if you connect descriptive model to analytical models, then you provide system architecture variants, configurations, you know, to the analysis, and you get performance outputs. Then you can do verification of requirements, you can do trade studies, and you can do optimization on your system architecture. That would be the goal of system engineering, to get optimal system architecture.
So others, what do you think? How do you think about different types of models?
Well, I know for the area that I'm focused in, for design and prototype, for example, we have a significant amount of models that we deal with that cover all the different domains of aerospace exploration, design, as well as analysis and simulation. So it's connecting information from these models between the different engineers that communicate with each other, whether it's the mechanical team doing the structure, or we have our power team and our electrical team and harness, our environmental control and life support teams. So those are different domain specialties. And then you'd have different models in different reviews from different viewpoints for people who look at this from reliability or system safety perspective, from an operational perspective. But the complexity that I know I always work with is this has to be something that works across our entire life cycle too. So while certainly I'm focused in models that we do in design and development, when we can't always test in the environment that we operate in. So yeah, other models, by the way, models of the environment that we plan to fly in and to be in. I also have to worry about, well, what are the other models and the other parts of the system I have to connect to in order to build and in order to launch and actually to run. So I think there's so many broad definitions depending on your vantage point of what part of your system or mission you're working on too.
Great. So let me dig in on that one a little bit more. And this is for Francesco or anybody who would like to respond to this. So, you know, and Stephanie, you're describing a pretty common scenario, right? We have different kinds of models for different domains. We have different teams that work on these with their models. We have naturally different modeling tools, right, for different domains. And these models are in their modeling tools, and we have all these different models. And so we're thinking about how do we hook these models together? My question is that an inevitable situation? Is this the only way? Or is this, because it sounds hard, right? All these different models that are different tools, different technologies, and we have to hook them together. Is this an inevitable way things have to be, or could there be other ways?
To me, yes. To me, it is a little bit inevitable, because every model needs to have a purpose. The purpose of many of the simulation and analytical type of models is to respond to specific domain questions, like optimization of maybe an antenna pattern or thermal behavior of your system, or maybe data flow in a complex network. So it's always responding to some specific domain question. On the other side, the what Saul called descriptive models, they have a rather different purpose. That purpose is to create a unified language, so to allow stakeholders coming maybe even from outside the project to understand what is the structure of your system, what are the interfaces, what are the components. So again, different concerns, different purposes, and different models.
All right.
The real challenge, I think, lies in integrating those models. So having an engineering effort where different models interact with each other.
Right? I fully agree with Lucio. It is inevitable to have different types of model, and actually, in my opinion, this is not a problem, or it should be not treated as a problem, but as an opportunity. Diversity is an opportunity to better answer to diverse objectives and purposes, as Lucio said. So we need to embrace this opportunity and to understand all together how to align this bunch of diverse model and how to make them working together, how to connect them, how to integrate them. And I think that the first step is really to use the definition that is provided in the ISO systems engineering vocabulary. Actually, there are a few definitions from that are used in different situations, but a couple are really, for me, very clear and actually usable. The first one says that is a complete description of a system from a particular perspective, and another is a representation of a system of interest from the perspective of a related set of concern. And these two definitions, they really emphasize that model is a representation, so an approximation, but is a sort of reference, and it serves to respond to specific concerns, and that's a key point for me.
So on,
Yeah,
go ahead, Stephanie. Yeah,
I was gonna say, I would agree on that point, because I think part of the reason we have different tools, different software, and different approaches for solving some of the different parts of these problems is because we have different specialities and we use information differently for different parts. I wouldn't want to confuse somebody with a radiation spectrum that they don't know how it affects, and maybe it doesn't affect the work they're doing in a certain part of the vehicle design, and yet I know my thermal analyst needs to know it. So it's at the same time where we don't necessarily want silos of information, we want integrated information. It's understanding when are those interfaces needed? What is the view that you need, so that you're not creating worse solutions or more confusion by having more data than you yourself or any individual decision maker knows how to handle or how to use in the right way.
All right. So, and we have, thanks for the questions. By the way, you can put questions in the Q&A and we'll weave them in here. We've already got a couple that we'll be getting to in just a moment. But let me go to this next thing. How much modeling should we do? Sometimes in talking to systems engineers, you get the impression that there is no such thing as too much modeling, that we should do all the modeling we can possibly come up with. And everything that could be modeled, we should model, right? So, and of course, some people say, well, that's great, but that will take too much time. Do we really need all that? So how do you know how much modeling is the right amount?
Very, very interesting point. Very interesting point. You should really stop when you realize that your engineers are more concerned about how good the model is and not in how good your system is. So, well, there is no rule. There is no rule, but in general, if you have clear what is the purpose of your model, you have a hint of when you have to stop. When that purpose is achieved, then additional work will not give you a benefit. You will reach a plateau where the effort placed, if, for example, your model was to do some simulations, some analytical simulations, when you have achieved that purpose, that is the moment to stop. Putting additional effort in making more detailed simulation just for the purpose of doing it is something difficult to stop. The modeler gets affectionate with the complexity of what is their achievement. But that's my answer. Knowing the purpose can give you a guide.
Maybe somebody else would like to weigh in on this one too, but just to extend the question a little bit, what do you, and I think this is important because I often hear people, systems engineers, feel like they need to defend the modeling that they're doing, right? And why it's needed. And what do you say to somebody who says, somebody from software or mechanical or anybody who says, look, it's nice that you're doing these models, but we got to get to work. So we're going to start building this thing over here, and because we got to get it built. We can't wait for you to do all your modeling.
No, but that's natural. That's actually why we need the modeling. And then also like we could think about this as a different role as who writes requirements, right? Like if we talk about the again, you know, like models as a requirements, right? And the model is created to understand the system, right? So we need to model as much as we want to get confident in that understanding of the future system or current part of the system if we don't understand. So I don't think that we need to model everything at the same level. If we know that part, we don't need to model. We can leave it as a black box. And if we don't improve that part, for example, as part of our project. So if we want to improve something, we need to model until we understand, until we have that understanding of the behavior. And then we pass that to the design. And we can't model design because we are not designers as a system engineers. If you are a designer, then do the design. But if you are not, then leave that. And that's like the same problem with requirements. You can't specify, it's even the wrong word to specify. This is requirements for the design, right? But not the design of the system. That's very clear. We should be careful because we have the people even coming, you know, from the DoD and big companies, and they think that requirements are actually specification of actual system, and that's like user need. That's like completely not, right? Like the need is actually what you want to get from system, and specification is what you will receive when the design is over, right? So not over specifying in the model, that's another thing, and that's actually why we should not extend the model more than requirements if we do the description of the system.
All right. Well, let's go to a question. Sorry, Stephanie, go ahead.
No,
comment on that.
I was going to say, I think that kind of also gets at the point of the too much or not enough. It's also the question of well done. It's not too much if there's continued feedback, purpose, there's moving on, but it's part of even just breaking out of the document centric, and the reason we have models, right, is that we can change them easily. But we need to be willing to change them. We need to be willing to say, okay, it's not stamped, set in stone, and now I'm just writing change notices or the reasons why, or the defect assessments, or why I'm not going to meet that requirement. It's well, what does it take to change the requirement? The idea is that it should be easier to change the model and have everything be reflective in the different associated models versus stuck with the paper that you can't change, or it takes so many signatures to change that it's not worth changing.
There's another part of, oh, sorry.
Please, Saulius, go ahead.
I just wanted to add quickly that from my experience in software domain, I noticed that, you know, implementing is one thing, defining what you want is another thing. And when the engineer says it's enough with requirements, like software engineers, like, let's do it, because like they are afraid that you will ask for something more than they want or they can. And that, I think, extends to an engineering, you know, there's human, you know, like wants to stick to what they know, right? And let's do it as I know, and then let's see, maybe it's okay. You might not know that it's okay, right? So that's kind of.
Yeah, in my experience, it becomes difficult to define the end of the modeling effort when the used approach is to try to copy the reality. And if you do that and you really try to make something equal to the reality, then there is no end, because there is always something that can be understood and can be implemented into the model. Differently, if we understand at the beginning the objectives of the modeling effort, and we ask ourselves, which are the objective of doing this model, which is the use that we will do, which are the answers that we have to provide to our team, and then basically you set at the beginning the criteria to establish when the modeling effort is finished, is completed, and then we'll facilitate a lot the work. Another experience that I would like to share is that, for instance, in science, actually, we try to increase knowledge. So we try to copy the nature. So it is an endless effort, because we continue to add knowledge, but also in that case, we need to face this learning journey. In industry or in other domains, when the goal is to complete a project, to deliver a product or something like that, it is really important, since at the beginning, to establish the role of the model.
Very good. All right. So I think the answer we've arrived at so far is how much modeling should you do? The answer is the right amount. But in that answer is you have to consider what is the right amount for the project and for the needs and so forth. So that's useful. Maybe sometimes that doesn't get enough consideration. What is the right amount, you know? But let's move on. I want to go to some of our questions here. So Joseph Lam asks, what architecture frameworks do you use to structure your models? And Lucio, I think you wanted to respond to this.
Sure, absolutely. So, well, there are many different architecture frameworks tailored to the different domains. It's quite a long journey, a long history of architecture frameworks. I personally like a lot the UAF, the Unified Architecture Framework. It's been an effort to take typically space and defense oriented frameworks and turn them into a domain agnostic, so into a framework that can be used equally for defense or for commercial and other purposes. And I find it quite well structured and easy to understand. So if I had to pick one today, I would say the UAF would be my favorite. Of course, there are different aspects of a framework that you may want to use. I find that the categorization of views, it's an aspect that can be even used alone. You may use the architecture framework to just identify what type of views you want to develop and for which stakeholder, and that is enough. You can add more and adopt the meta model and the more detailed structure of the framework if your tool provides you with the profile for that, and then you can add to it. So there are, as in modeling, also adopting architecture frameworks can be done at different degrees.
All right, very nice. Let me throw another one here. Matthew Jones has an interesting question. What guidance would you give to support the coherent management of multiple interacting models? And so several of you touched on this already. What would you create a model of models, right? I used to use that term a lot, right? And what would that mean, right? Do you need a team focused on model governance? So how do you approach that sort of thing?
So like Lucio well defined that it's like UAF, it's model of models, right? Like systems level, right? So you model what systems you will have, how they contribute to your solution, to capabilities, what you want to achieve at that moment of time, right? That's why it is enterprise architecture, which you define with UAF, and how that will evolve over time. So it's like model of models. Another model of models is how you will version control your models. And that's how they trace and how you pretty much baseline them for a specific project, right? Or level or time, right? So that's another thing. And traceability tools should work together with analysis tools and system modeling tools to define that, models baselining, which is big part. And definitely you need to have someone responsible for that. It's like release architect, right? Who is releasing DevOps engineering, software engineering.
Yeah, and I would agree that some sort of model governance and even some sort of data governance is an important part of a complex program, especially like what we're talking about for whether it's telescopes or space vehicles or space stations. There's a certain amount of data that we already think about doing as far as configuration management around just milestone reviews, but certainly the in development parts of the system and the entire life cycle of the system are not just those milestones where you understand exactly what the management of the status of the design or the impact is. It's not the same as like with commercial electronics, having here's my user guide, here's exactly what is in that exact build. Yes, we need that, but it does change over time, and it changes throughout the development. So I think having some sort of understanding of your model governance and what phase in development you're at, whether you're in conceptual mode or whether you're getting to a design phase that you're really moving to hardware, towards manufacturing and build, it changes. Some of that governance changes. So having some idea of how you're maturing or changing your model governance, if you will, it is rather important, because that curation changes as your life cycle changes.
Let's do one. Sorry, Francesco, go ahead if you want to comment.
Yeah, I mean, regarding the challenge to integrate system and discipline specific models across the life cycle, I have experienced a couple of situations that I would like to share. First, it is fundamental to establish at least a shared business glossary. So to make sure that people use the same terminology in creating these different models. And second is to create awareness about the proper role of systems engineering respect to other engineering disciplines. Otherwise, there is the risk that the system design emerge from pieces and not from a shared concept and architecture. So I know that there are also technological challenges, and I will let the modeling expert to say more about that. From a managerial point of view, these are the two major issues to really bring people towards the same direction, and to have a shared understanding and a good communication in trying to integrate these different models.
So a couple of people have mentioned SysML specifically in their questions. So I want to kind of wrap this together. And I think this is worth diving into, even go a little more level of detail here. So I like what, oops, and it just scrolled off my screen here. Julia, Jose says, SysML is a complex language. I don't think anybody denies that, right? SysML is a complex language, and it's not just systems engineers that need to understand how to read the model. Other domain experts need to understand it too. What can be done to reduce this complexity? Are we considering languages other than SysML, or, and then Joseph comments, SysML is a specialization of UML. You could also wrap into your answer, how does this change with SysML 2? And where are we going with this? So what do y'all think about that?
So maybe to add, this is discipline language, right? So it is for systems engineers. And we always think that we need to be at the same level as the managers will understand, or like whoever director, will understand without expertise in SysML. This is not true. We need a discipline language to be efficient in whatever we do as a discipline. That's what you have in the, software. They have their own methods and they have their own things. That what you have in electrical engineering, and no one tells that, oh, now suddenly everyone needs to learn electrical engineering. So okay, get degree, then you will learn. And complexity is there, right? Because you need to be efficient in that engineering. And it's not up to someone to decide complexity or not, unless you are a system engineer, then what you need to do and how to do it. Another thing is that SysML produces outputs, as any discipline produce outputs for the dedicated roles, and that role should understand whatever is produced, so that it's responsibility for system engineer to produce that output in the language or whatever method that it would be well communicated. Could be automatic output. What we see, in SysML 2, especially, comes as automatic outputs in many cases, because you can make the query-based, web-based, Confluence views. I saw already some prototypes of that generated, and that could be simplified views,
So Saul says some of the complexity is warranted. It's a complex business, and yet SysML 2 is trying to become less complex.
I don't believe that.
You don't think so? Okay.
No, at all. Not at all.
If I can comment on that and share my experience, I truly believe that the success of model-based systems engineering has a strong dependence on the capability to communicate with all system stakeholders, and an effort that we engineers should do is to not stop on the engineering effort, to create a SysML model and check that everything is fine. That's not the end of the story. We should communicate during the preparation of the model and also after the model has been completed. My experience that in my scientific community, it was really challenging. And so it was extremely important to involve people when we need to create those models, for instance, an activity diagram. You know, you talk to the stakeholders and you involve them, and they feel like they are part of the team and they are somehow contributing to that development. Then when it's done, we need to do the effort to translate what has been done and to make it readable to all stakeholders. That's really a step that for me is mandatory. Otherwise, we lose the value of model-based systems engineering.
Another thing,
right.
you don't need to use all the constructs of SysML or SysML2, you know, like you just use whatever you need to use, you know, no one tells you that. Actually, if someone would use extreme sides of SysML, no one ever would understand the models.
Well, that may be the word. And in fact, it's the same in any language, right? I mean, most of us do not use the entire English language, do we? We use a small segment of it, right, most of the time. But let's move to our main topic here. Let's move into space here. Okay. So the question here is, what's different about space? You know, we understand we do models, we do MBSE. Is it just the same when you're working on space systems? And here's space systems, as you can tell from the intros for everybody, some space systems are on the ground and we're looking at space, right? We're dealing with space, and some space systems are going into space. They're spacecraft, right? So how do models apply, or what are the special concerns of modeling in space?
Well, certainly for one thing that I think I mentioned earlier, it's the environment. We don't have a way on Earth for a lot of the things that we do send into space to do a test that is relevant to the exact operating environment or all environments all at once, all at the same time. We can maybe test some parts of the thermal experience or some amounts of radiation or some amount of gravity forces, but we don't have that same thing as being what we'd say it's in situ, on site.
I think Stephanie may be having a connection problem. So somebody else want to pick it up there, and we'll circle back to Stephanie.
Yeah, I can add something. So the main purpose is really that the system is not reachable, is not directly maintainable with an operator fixing things. So you need really to make sure that everything works before you deploy it. And I can bring also some experience on that on land-based systems, like radio telescopes, like those that you see behind me. Radio telescope, they don't go to space, of course, but they are still built in radio quiet zones, so hundreds of kilometers away from cities. And the effort of delivering an operator to fix anything, it's still significant. So what you really need is to de-risk any trouble that can happen on site. So that's why modeling is essential. And I believe all types of modeling are essential. So performance, simulation modeling, you want to make sure that in your lab, you can reproduce in a small prototype or in a CAD model anything that can happen with the operational environment of a remote, maybe.
Very good. So I think to put this together, and then we'll circle back to Stephanie, who had a connection dropped, if she wants to continue. But it sounds like we've said, all right, models are necessary in systems engineering, lots of models and so forth, and they're even like more necessary in space systems because for certain reasons of precision or reliability or environments. So Stephanie, you want to pick it up there? Is there some further thoughts along those lines?
Yeah, and I'm so sorry about that. I hope I don't get dropped again with my connection here, which I thought was stable. But I think the challenge certainly for a lot of space is that a lot of what we're trying to do, it's not something we can just go outside or go to a building or go to a room and have the exact environment, the exact experience on our vehicle or spacecraft of what it's like when you're actually in space. So it's how well can we understand with a model what that environment does to our system, and understanding multiple parts at the same time. I might be able to expose to the different temperature swings. Maybe I can do something about gravitational forces, but it's very difficult to do something that is representative of temperature, gravity, radiation exposure, all of these things at once on Earth. It's something you have to do in space, but I also need to make sure I'm not sending something up that is unsafe to other vehicles or other space programs, or that I can sufficiently launch it. So we rely on models a lot because of how difficult it is to do things that are just in test form on Earth.
And so how this came up before too, how do you validate those models? Because you can't, as you said, compare it to the real phenomenon. We can't take it out to, you know, space for a moment and see how it operates and see if our model is accurate. So how do you handle that?
Right. I think that's the challenge that I think is still ongoing and still developing. And I think it's where, certainly in space, it's where a lot of the digital twin concepts come from, is what can we use with sensor data from existing satellites, data from previous missions? How do we use that to feed back into how we model the environment, and then use that in our overall mission models and simulation? And how do we keep updating that information and getting more information from those? Whether it's, like I said, actual sensors on things that have already gone before, or whether it is how much we think we can recreate the environment here and then get more data to utilize. That's certainly one feedback, and that's models in and of itself, right? It's models to help validate the other models.
Like calibration, right? So you can calibrate and see how precise is your model. If you can't calibrate, then okay, then good luck.
It's some amount of calibration, some amount of validation. I mean, looking at models of the environments between the Earth and Moon and Earth and Mars and what we have over time. If you look at the different missions that NASA has done, or JPL, how do we take some of the sensor data that has been used to understand, well, what's really the impact of a high solar flare year on a mission? And how do we incorporate that when we're looking at survivability of radiation shielding on a spacecraft? I mean, I've just dove into some very specific cases or examples, but these are the things that aerospace engineers who are working in space exploration, or even manned or unmanned as well, both whether it's a manned or unmanned mission, have to consider when they're trying to design their system to still meet the mission objectives.
This is a good point, you know, so you have that data, right? And then you can run the model against historical data. So like, for example, in finance, if you build a model how to deal the stock, you know, like if you work for the big company, you always run the model against, you know, historical data and see how that model performs, right?
Right.
No,
but this is why we have so many partnerships in space, right? It's why we have an international space station, so that we can hopefully have sensor data from all of our partners on that, versus the ones that only a specific company or country have sent.
Well, I think this is putting some meat on the bones of what we said earlier, of models have to have a purpose, right? And some models, their purpose is to describe something, right? So just to be able to communicate it. So maybe that model is worth the effort in order to be able to communicate something. But as Stephanie's indicating, some models have a purpose of trying to help us learn something. We want to learn something about how the system performs in an environment or something like this. And so that model earns its weight, it earns its cost, right, by teaching us things. And so the acid test is, did we learn something from this model, or did we just do a nice model that completely proved what we already knew, you know? And does that really help? But I like that Stephanie got real specific with her examples. In fact, a bunch of our participants here are wanting us to get more specific, I think. So I'm going to call a little bit of an audible here and ask the panelists to even be a bit more specific about what kinds of models you're doing in your environment. What do you see as valuable? What tools and methodologies are you using for what purposes, and what are you learning? What are some of these lessons learned from what you're doing in your environment that could be valuable both in people in space, not people in space, people in the space industry, I should say, and other industries as well?
Oh, let me give you an example. In in this telescope that we are developing, we have the circle that you see here is about 40 meter diameter circle of 256 antennas that we call a station. So in order to optimize the performance of that station, electromagnetic models for generating the complex antenna pattern that comes from that has to be modeled, coupled with thermal behavior models, because it's metal wires exposed to desert type temperatures in a harsh environment. So combined models were developed to take into account the electromagnetic side, the thermal side, the mechanical distortion side. And so hybrid modeling has been done. But then the crucial part, validation, we need to develop a prototype. So our entire project is made of stages. We don't build it once at a time. We do a prototype, we validate those models with real observations, and we possibly even study different layouts. We can arrange the antennas in many different patterns related to each other. We need to simulate them first, because when we go to the desert for our prototype, we can do a prototype every couple of years. So a lot of simulation, optimization, but then the real world comes when we do the prototype, maybe 2 different layouts, and then we compare them. This is precisely the activity that we are running now.
I think everything will be virtual, because prototyping is okay, but you don't have ability to prototype like millions of possibilities, which is possible with virtual. Like Tesla, I remember, like they said, oh, we have the fleet of cars, millions of cars. We will gather the data from the streets. Now we will have all the data. Now we will be the fastest to produce AI. And how they do the 10 times more, maybe even more the virtual testing. So looks like not enough to have the biggest fleet of cars.
In our case, I think we are implementing different types of models. We are doing engineering models, as Lucio said. We also try to model the telescopes that you see on my back. However, the engineer system doesn't end with those, let's say, optomechanical structures, because we are looking for gamma rays and they cannot be detected directly. So what we do, we try to record the secondary particles that are created in the interaction of a gamma ray with the atmosphere. That means that the atmosphere is for us a kind of calorimeter, is part of the system. So in the model, we have not just the description of the telescope itself, like the mount, the optics, and the photosensors, the imaging camera, but we also include a description of the atmosphere, because it's part of the detector. Then this basically is a model of the instrument that we are using in order to answer our scientific questions. And of course, what we want to do, we want to increase our knowledge of the universe. In that respect, we also model the universe, so a natural system. And at a certain point, we need to connect the engineering model and the natural system model. And that's really challenging, but it is mandatory if we want to increase our knowledge and to understand how the nature works.
All right, this is good to getting into the more specifics here, and I think we'll stay with this just for a moment and then move on to another kind of topic. If you notice, panelists, a bunch of the questions that have to do with there's a whole group of questions that people are like, want some career direction. In other words, okay, I'm a new systems engineer, or I want to know what to study. It seems like there's a lot of things out there. What should I focus on, now to kind of build my knowledge and so forth? Who has some input along those lines?
I get that question all the time. Yesterday I got the question, how to pass exam, for example, for system engineering. And that's like fundamental. So one thing, pass exam, for example, for system engineering. And there are 2 exams if you think about model-based system engineering. One is the INCOSE, right? System engineering certificate, ESEP. And why it's good? Because it talks about all the parts of system engineering, whatever you can do, like in system engineering. And that's like very traditional approach, but like that's the 60 years or plus, experience-based approach, right? And then another one is model-based system engineering. And I think the best one is SysML certificate. Why it is like SysML? Because that's like 10 times more used language than any other language. And the most people like consultants, trainers, tool vendors work on that language. So the most papers, like 100 times more than any other language. So those certificates will require you to learn, and then you can read books like Sandy Friedenthal and Delegate and the System Engineering Handbook for System Engineering. That's like by yourself, because not everyone goes, for 4 years to school, but also not everyone has a work in good team for system engineering, which would be the best for sure.
I'd say learn how you learn, because you're going to need to learn new languages throughout your career. There isn't one language that I've been using the last 5 years that I learned when I was in college 25 years ago. Yeah, more than 25 years ago. Python, I use Python now. It wasn't a thing then. That wasn't a language. So SysML was not a language then. So the biggest thing I can say is don't fixate on knowing one super in depth. Barclay already made the point that we use a fraction of the language in what we do, even in English. I love my Duolingo for when I do travel for INCOSE, because at least I can learn how to get around with the different chapters and try and not just rely on English. It's the same way in technical work too. So know the language that is of the moment now for the domain you're in. Saulius already covered that brilliantly in terms of know SysML, look ahead to SysML version 2, but know the other languages that you need to communicate with, for the other people you need to communicate with. I know what to look for on a drawing. I know enough geometric dimensioning and tolerancing, GD&T, for example, so that I understand how non-functional requirements relate to that kind of world, but you do not want me driving your CAD or doing your mechanical design. That's not a good thing. And I'm not going to keep up with the standards they have for that. So make sure you are learning about what languages you need to know and what other languages you need to know a little bit of, because it's great to script a little bit in Python, but I'm not writing flight code either.
Well, I'll add a +1 to Python and cap it with a little story. I was at an INCOSE conference and at breakfast, and a friend walked by and I said, "What are you doing today?" He says, "Oh, I'm going to a big thing on digital engineering, digital twins and stuff like that." And so in my little snarky way, I shot back, "Oh, so you're going to be teaching them how to do APIs with Python?" And it kind of took him aback, and he said, "Well," and he kind of laughed and he says, "Yeah, it does boil down to that, a lot of the time, right?" But so definitely +1 on Python, and not to turn systems engineers into software engineers in my view, but to make Python a tool for systems engineers to be able to do things that they need to do. It becomes a tool. So, all right, let's see. Let's go on to kind of our final main topic area, which is the future, the undiscovered country. Did you get that? 2 Star Trek references in the same webinar. Okay, so in the this is an invitation for the panelists to dream a little bit, to kind of look toward the future and say, all right, here's where we are now in terms of MBSE and models for space and so forth. And we expect this all to go into the future. We expect a lot more space travel in the future, space exploration in the future, inhabiting other worlds at some point, we think, right? The moon or Mars or wherever, right? And how do we see systems engineering evolve? Do we expect it to be SysML version 7, or will something else have completely eclipsed it? See another space reference there. But anyway, where do we see this all going in the future? What do we need? What are the gaps? Do we need new kinds of tools, new kinds of languages? Do we imagine whole different ways of doing things in the future, or we want those?
I think one key thing is that we lack of engineers, and that lack is not like a little bit, it's like we lack like 10 times as we have. I think that's the problem. And, everyone wants that kids would be successful, right? And there is no better career than engineering, I think, because it's very predictable. If your kid can build something, let them build something. And most of them are very creative, very art-oriented, very kind of structure-oriented. We want to see things happen. And there are, like, for example, schools like Code Ninja. They do Lego robotics, 3D printing, and programming at early stage. I think that would be amazing future, you know, because engineers don't destroy things. And also, you know, they want to build things, you know, so, and our future would be much better if we would have more engineers.
From my side, the future of modeling, I don't want to look far away. Everything, I mean, something amazing will happen that we cannot predict. In the immediate future, to me, the word is integration. I see an immediate need of integrating models. That's digital thread pushed forward, making descriptive models completely integrated with performance model from many different disciplines, managed by AI and virtual reality to recreate the experience from the engineer to the user seamlessly. So the engineer needs to feel the same feelings that the user has when they use the system. This is a better way to engineer that system by sharing the experience. And so the model should allow the engineer to do that.
There was question, actually a few questions on virtual twin. How can it be like virtual twin without real physics, you know, like, I mean, like without being real world. So, you know, my daughter plays Roblox and she can build a game in Roblox. So that's the best virtual twin I think you can get, you know, except maybe the physics coming back, you know, but like, again, you know, that virtual environment, Lucio, I think shows how that should be in actual world for us, you know, as experienced engineers.
In my opinion, I see a future where standardization will increase, automation will also increase, and industry will provide tools that can be easily integrated, and data and information can be exchanged. So in the future, I can imagine that the modelers will be facilitated in developing correctly the model. However, there is still the need to understand how to properly respond to the stakeholder concern and needs. Of course, when those are well defined, we can also use artificial intelligence to identify the most accurate and the proper decision to be taken. However, we really need to, also in the learning journey, we really need to not forget that at the end of the day, these models, they have to be, they must be used to respond to the stakeholder concern, expectations, and needs. And that's something that for me will remain on the human side.
Yeah, and I think similarly, we have a lot of initiatives at INCOSE that look at the future of systems engineering, or our visions, the Vision 2035, and previously we had Vision 2025 and such. We change those way before we ever get to that year, because we see how much it's going to change before we've gotten to that year. And I think that's still holding true. I think a lot of what we're doing with models now, whether it's the integration that Lucio has meant, or the responsiveness to the stakeholder, like Francesco said, and to some of the other parts of the model basics that Saul said, we're going to find new and different things as we're doing this. We've been accustomed to making sure that our specialties understand what they're doing and we know what flows from one domain to the other. We very much have segregated things out. And now what we're trying to do is find better ways of bringing them together to understand more of the dependencies, to allow dependencies that we tried to make independent before so that we could get work done. I don't know that we understand what we're going to find when we do that, and if there's something that will change the way we work as we discover that.
Well, a number of you have mentioned integrating models of different types, and it seems, I mean, I've worked in this area too some. It's difficult, to put it mildly. And I'm wondering, you know, where do we see that go? So yes, we all talk about how that's part of the future, but how's that going to happen? Slowly
yes.
and painfully, he says. Okay.
Sometimes fast and painfully too.
I think KPIs is one of the key tools for that, right? So having, you know, understanding that there's no model to rule them all. You cannot have a single model for everything. Every model stays in its own domain and use its own logic and purpose. But then through exposure of APIs, you can provide to the other users your information in a way that makes that model independent from all the others. And so creating this network of knowledge is actually the integrated model, not a centralized, a decentralized set of models talking with each other.
That's actually a value of SysML2. It has standard API, standard execution, and simplified semantics, which is like definition and usage.
Which enables it to play in that kind of environment. I mean, I love what you're saying, Lucio, that in a way, software has sort of solved this to some extent, right? That it's not by centralizing, combining all the software into one ball of software, but letting these different software elements talk through APIs and maybe modeling models or something similar. Easier said than done, of course, right? But it's an interesting pattern, right? It's more instead of a model of models, maybe the better term is a network of models, you know, with the models talking to each other in various ways.
And that's a concept that's interesting and good, because a network of models can also help with the troubles or issues that you have when you're trying to protect IP, or how you can collaborate with your teammates that are at different companies that are sometimes your competitors on certain contracts for space. Very
good. Well, let's quickly, in just a moment, we're going to move to brief concluding comments from each of the panelists, so you can be thinking about that. But I will also throw this out as a career direction. Those of you looking for some career directions or some research directions, you're looking to PhDs and so forth, model integration. You notice when I asked that question, the panelists were stunned and silent for a moment. What that means is, and this is not a criticism of them, this is that this area is not figured out, right? There's a lot of work still to do in how do we connect and how do we integrate models. It's a great topic for research and for to focus on in your career, perhaps. So concluding comments, starting with Stephanie.
Space is fun, but it's complicated. So we need models.
Well said. Saul.
Yeah, so this community actually created a model-based system engineering. Somehow I believe that, because I saw even before SysML, there was like the telescope group activities and papers. So, and they, I think, will continue leading, because they on that mission critical side with the opportunities to show, to convince everyone that it will not fail until it will reach the destination.
Right. Very good. And Francesco?
Yeah, I mean, I think Models in Space is a very good lab for learning all types of models, all different usages that can be performed with models, and also a lab for combining engineering and natural models. And I also would like to emphasize that, for instance, in our case, the model is the final artifact. We model the universe, and that is what we will pass to the next generation, the model, not the telescope. The telescope will be retired, and at a certain point will be, dismantled. What we will pass is the knowledge that is explained through models. So that should motivate people to invest on that, and to invest on the journey of moving from descriptive models that where we are very strong right now, predictive and prescriptive models. So I think more work on prescriptive models should be done to really allow people to take the right decisions in the future.
All right, very good. And final quick comment, Lucio.
Yeah, I think space is in need of models. We cannot go to space without models. And we cannot look at the space without models. So, yeah.
All right. Well said. So let's just wrap here. A couple of quick notes. Calling All Systems is a series of these kinds of programs. You'll see the future ones to sign up for at incosi.org/callingallsystems, just like you would expect. So go there and see about the next programs. If you're not a member of INCOSI, of course, we invite you to join INCOSI. You can go to incosi.org/join to find out how to join and the memberships and that sort of thing. And of course, stay with us, get involved, and we're glad to have you in the community. So for Calling All Systems and our marketing department in Nkosi who's produced this, Honor Lynn, Emma Jane Taylor, and their teams, we appreciate that. And thank you very much to our panelists for taking time out to share your wisdom. And we'll see you next time. Have a good day.